Hello guys, good morning. So today we will discuss a very interesting problem. The problem really intrigues me because of the relationship between certain random variables. Okay, relationship between random variables and distributions are one of my favorite topics. This is also related to something called Box-Muller transformation. So what it really tells, what are the four distributions that I'm going to talk about today? The four distributions are the following. The first one is a normal random variable. You must be knowing about it. It's very famous among peers. And we will see another something called Cauchy. It's the normal Cauchy. Location is 0, 1 is the scale parameter. We'll see the relationship between this, why this is so natural. Okay. I mean, when I was a student of undergrad student, this doesn't seem natural to me. Okay. But when I was I came to know about this Box-Muller transformation and this property, this really something really awesome. Okay. And then there is something about the uniform, which is sort of related to every sort of distribution, but I will today connect it to the Cauchy because of this certain scenario. And also along the lines of what? Along the lines of the distribution of chi-square, which is related to normal 0, 1. Okay. So now this four together forms something called Box-Muller transformation related to this, but let's see how it is connected. That's the next step. So that's the part where we come to the coordinate axis. But before that, let me share the problem that I'm going to discuss with you today. Okay, the basis of this discussion today. This problem today is a ISI MStat 2009 problem 4. Okay, let me share the problem with you. This is the problem. If r and theta are independent non-negative random variables such that r square follows chi-square 2 and theta follows uniform 0, 2 pi, then we have to find the distribution of something like r sine theta plus theta hat. Well, there's a theta naught, sorry. And theta follows uniform 0, theta, and theta naught follows is a number, it's a fixed number from 0, 2 pi. Now a question must naturally come to you, what is the physical significance of this number? Okay, why chi-square? Why uniform? Why are these various odd random variables out there? And you must be understanding, that's why I call the discussion about chi-square, uniform, Cauchy and normal coming out there. So now let's see how these come up so naturally. So what we will consider the basic idea of something. So the basic idea of coordinate system, okay, the polar coordinates and the basic coordinate system. So let's try to understand this. So observe this, that in this system, this is x comma y, okay, and the same point can be represented in a different format, where we denote the radius and the theta. It can be denoted as r comma theta 2. And it's a one-to-one bijective mapping. Okay, every point has a unique r comma theta, and every r comma theta is a unique x comma y. Okay, so how do we transform that? We transform in the following beautiful manner. So r squared equal to x squared plus y squared. Okay, and theta is equal to what? Tan inverse y by x, right? This is equal to what? This theta is equal to tan inverse y by x, right? So this is the basic definition and basic relationship. Okay, so this is the basis of our discussion today, that how these four distributions are connected and how this problem, the problem where it's given, the various informations are given. So let's now go back to the problem once. The problem tells what? You have this sort of distribution of the corresponding aspect of r, where r is sort of r square follows chi-square 2. Why chi-square 2? That's an interesting question. And this theta follows uniform 0, 2 pi. So what we are doing sort of r square, we are randomly selecting r square, which is sort of coming from chi square 2, and we are randomly selecting this theta uniformly. Okay, 0 to pi 2 pi. Sort of we are selecting 2 points. Okay, sorry, 1 point 2x. So this we are sort of selecting this point out there. Okay, we are fixing that point. Now, why the relationship? Why chi square is coming up? So let's try to understand this a little bit more in details. So consider this corresponding line. What we do, we have this x and y, and x, if it follows normal 0 1, and y it follows normal 0 1. So essentially we are choosing x comma y following the joint distribution following bivariate normal, okay, standard bivariate normal, okay, that is the z1, like with this 0 comma 0 and the variance covariance matrix as 1 1 0 0. Okay, we are selecting with this. These are not correlated with one another. So now if we select like this, then what will happen? You know that the relationship between x square plus y square, that is r square, will follow what? The independent normals. Okay, the x square plus y square will follow what? It will follow chi square 2, because summation of independent standard normal square follows chi square. Okay, and what else? We know that y by x follows what? Cauchy 0 1, right? That's the beauty coming up. Y by x follows Cauchy 0 1, and we must be knowing this result that tan. So this is the relationship. So now comes a relationship with Cauchy and uniform. Okay, this is a relationship. So what is the relationship with Cauchy and uniform? So Cauchy, standard Cauchy norm, the corresponding the density function is like this. And if you see the distribution function of Cauchy 0 1, it looks like this. It's sort of arc tan, like tan inverse x minus half 1 plus this, most probably this. So now essential my viewpoint is the following, that if u follows uniform 0 comma 2 pi, not 0 comma 2 pi but 0 comma 1, then tan of pi into x minus half, sorry, u minus half follows Cauchy 0 1. This comes from the relationship that any distribution function of any random variable x, where f is the distribution function of f, follows uniform 0 1. X follows uniform 0 1. So x has a distribution function of f, and f of x, therefore the random variable, follows uniform 0 1. This is really important behind a simulation of many random variables. Okay, so this is really important, okay, in the sense that x and uniform, any random variable and x, any random variable and uniform theta 0 comma 1 is actually related in this manner, in this aspect. Very good. So now what's next? Next part is, so this is the relationship. So as I have told, if you see, I have told that we have got the relationship between normal and Cauchy, how x by y. We have got the relationship between normal and chi square, like x square plus y square. And we have got the relationship between Cauchy and uniform, tan of Cauchy. The sort of tan of uniform follows Cauchy. Okay, so that in that sense. So this is the basic relationship between all these random variables. Fine, very good. So now, but we are assumed in a different manner. We are assumed in a manner that if x follows normal, then what is the relationship? Okay, what will be the r, what will be theta, and that's similarly like that. But the given question is in the reverse order. It asks you that if r follows is x is chi square 2 and theta follows uniform 0 comma 2 pi, then what is x? What is x? X is actually r sine theta. Okay, and what is y? Sorry, r cos theta. And what is y? Y is actually r sine theta. Okay, this is the x and that is the y. So how to do this? How to do this problem? How to approach this problem? The problem, this sort of problems, so essentially when you have this sort of diagrams, this sort of one-to-one relationship and the variables are changing, the only possible option is what? The only possible option is Jacobian. Okay, we know this distribution. We are going to do this distribution. Okay, we know what R follows. We know what theta follows. Therefore, we are going to do what X and Y follows. Okay, that's the basic idea. How X and Y like behaves with one another. Okay, I hope all of you got this point. Now, what's next? The next idea is to understand what is Jacobian a bit. Let's try to understand a Jacobian a bit. So essentially, we are trying to convert in R theta to X comma Y, and why it is so. And what do you think? By the way, before proceeding ahead. See, observe that here R and theta, R square follows chi square and theta follows uniform, right? So here the given it's a condition is given same. So we are going to backward. Okay, so that means what do you expect? You expect that X follows normal 0, 1, Y follows normal 0, 1, and X and Y are independent. As rather correlation is 0. We can at least tell that. Okay, we can at least tell that. Okay, so this is our aim today. This is our aim, that how and why this is true. Okay, so let's try to understand this. Let's try to understand this aspect. So there are lots of different ways of doing it, but I will be taking the path of Jacobian. Okay, I will be taking the path of Jacobian because I love this one. There's another beautiful way using estimation by Debasso's theorem. Okay, which way tells the following, that since theta follows uniform 0, 2 pi, we can show that tan of theta by 2 follows Cauchy 0, 1. And there's a result that this is a beautiful result. This will imply that tan of theta will follow Cauchy 0, 1. This is a beautiful property of Cauchy. I really love it. And also R square is x chi square 2, and there we can actually divide it into sum of two squares where both of them follows normal 0, 1. Okay, and now we can actually show that this sine theta is sort of similarly distributed as x by root over y by root over x square plus y square. Okay, so you can actually understand this is a very beautiful property. So this is what we are going to establish now, going to do now, but we will be using Jacobian. And this sort of independence and stuff like this, there's a beautiful result of Debasso's that tells that for any estimation, it's a path of estimation. If you're estimating theta, any parameter, then any complete sufficient statistic of theta is independent of any ancillary statistic of theta. Okay, so this is a beautiful theorem. Using this, we can find independence and prove independence of any two differently unrelated estimates, like statistic. Okay, estimators. So this is a beauty of a Debasso's. So let's not digress. Let's move on to the proof. Let's revise Jacobian first. So we will revise Jacobian. What is Jacobian? So essentially what we are trying to go from x comma y. Sorry, we are trying to go from r comma theta to x comma y. Now observe, remember I told you it's a bijective one-to-one relationship. Okay. Otherwise, we cannot really use Jacobian. There's a mathematical significance behind it. Why we cannot use Jacobian? There's a geometrical significance behind Jacobian. Okay, the Jacobian. So, what is a Jacobian? When you do this, suppose what you do. So then x is actually a function of what? X is a function of x of r comma theta, and y is a function of y of r comma theta. Okay. So when you do this transformation, then you do this parameter change, like the coordinate change sort of, what happens is that the distribution, the sort of not the distribution but the density function, let's not write like this. So yeah, this is a new density function. You can write it in terms of the old density function. Okay, and the other way around. So let's first list the relationship. R square is equal to x square plus y square, and what? theta equal to tan inverse of x by y. So what we are trying to find? We are trying to find this, right? And what we will know, we will see the relationship between r comma theta of r comma small say z. Okay, the r comma z. So what is the entire idea now? We are trying to understand that how these two densities are related. These two densities are related in the following manner. So what we will do is the following. We will do that. We will first compute, since we know the distribution, we will first compute r of theta comma f of r of theta comma z, like this r of theta, we know this. And what we will do is that we will connect this with f of x comma y. Okay, now how we do that? We do that in the following aspect, in the following manner. We show that this is r comma theta of r comma z. Okay, and we replace this r and theta in terms of this x and y's. Okay, in x and y's. So r is actually some r of x comma y, and theta is actually in terms of theta of x comma y. Okay, that's what we are trying to show, right? And rather it's like we are going from x comma y to r comma theta in that sense. And there's a Jacobian. Okay, what is a Jacobian? So since we are changing from x comma y sort of to r comma theta and r comma theta to x comma y, there is a relationship. So what is that relationship is actually measured by the following thing, by the following determinant, where we do dr of dx by dr of dy, and here we do d theta of dx by d theta of dy. Once we do this, we will get the Jacobian. It's a actually, and then there's a modulus over here. Okay, there's a modulus over here. So remember this stuff when we're trying to change parameters. This is the way out. So what we got? What is the result we got? We got f of x comma y, small x comma y equal to f of r comma theta z, where r equal to x square plus y square root over, and theta equal to what? Theta equal to z equal to tan inverse of y by x. What we are trying to do is that we will try to do that d of, we will take the modulus, we will take the d of r comma dx by d of r comma dy. The determinant inside the external is a modulus, and d of z comma dx and d of z comma dy. If you just compute this, d of r comma dx will come out to be x by root over x square plus y square. D of r comma y will come out to be y by root over x square plus y square. D of z comma dx will turn out to be most probably it will be minus of y by x square plus y square, and d of z comma dy will be minus of x square plus y square. Now if you compute its determinant and if you compute this, you will get that it's coming out to root over 1 plus x square. Okay, it is in terms of 1 by r. Okay, actually it's 1 by r. So what we will get? We will get the following, that f of x comma y is equal to f of r comma theta r comma z, where into 1 by r. Okay, this is the idea we will get. There is a dx dy and dr dz over there, but this is the basic idea. And then what we will do, we will replace the values of r equal to x square plus root over x square plus y square, and we will replace the values of z equal to tan inverse of y by x, and we'll see the connection. Okay, we'll see the connection. So let's try to see the connection. Let's try to do the calculation. Before that, we need to first calculate this, right? So now observe that we are given the information that r square and theta are independent. It's a bad color. R square and theta are sort of independent to one another. R square follows chi square and theta follows. But observe this is another thing. This is given theta plus theta naught. Okay. So I'm calling that together only theta. Okay. It follows uniform theta naught comma theta naught plus 2 pi. If theta, let's call it theta dash. If theta follows uniform 0 comma 2 pi, then theta naught plus theta naught follows uniform theta naught comma 2 pi. But do you think that will really affect tan? No, because tan has a corresponding period of 2 pi. That's why it will never affect that. Okay. So what will be the f of r comma theta? F of r comma theta will be, theta dash rather will be what? Theta dash rather will be, both are connected to each other. So what will be it? So if we will be knowing the usual, the corresponding chi-square distribution and the corresponding uniform distribution. And what we will be getting? We will be getting r by 2 pi times e to the power minus r square by 2. Okay, you will get this part. Where this is coming up? It's coming up e to the power minus r square by 2 into 1 by 2 pi. This is the part of this uniform theta dash. This is the part of the chi-square. Okay. So this is the independent, because they are independent, so therefore we can distribute their, like we can make their product, okay, work like that. Okay, so what we have got f of x comma y, small x small y equal to f of r comma theta dash rather r comma z times 1 by r. So we have got this, that r by 2 pi e to the power minus r square by 2 into 1 by r. And we are getting that r cancels. We are getting that 1 by 2 pi e to the power minus r square by 2. What is r square by 2? Remember, it's e to the power minus x square plus y square by 2 into 1 by 2 pi. Now, do you remember this distribution? What does this look like? It's look like standard bivariate normal. This is standard bivariate normal. And since this is standard bivariate normal, what do we get? We get that x and y are not correlated to each other, and x and y individually, the conditional distribution follows normal 0, 1, right? This is a bivariate normal, and therefore x and y individually. And what is y? Y is actually r sine theta dash, and x is actually r sine r cos theta dash. Now observe that adding some theta naught is actually not helping, okay? Really not helping out, because the tan of the distribution is actually same. Okay, and this product is remaining 1 by 2 pi, that's fine. So essentially adding something will not really affect it. So very good. So what we have done, similarly using the other way around, we can actually prove that how those corresponding x and y is related to r comma theta. If x, you know x and y, what is r comma theta? We can actually prove that r is actually chi square, you should know that, and theta is actually uniform distribution. Okay, you have to find that out. There's a little bit of calculation stuff over there, but you can easily find it out. But essentially you got the basic idea, that basic relationship that I was trying to convey to you. If you take x comma y, if you take randomly select x and y to be normal 0, 1 and they're independent sort of, then what will you get? Will you get that r square equal to x square plus y square sort of chi square. So this is chi square, and theta is sort of uniform, okay, and tan theta is Cauchy. So this is a relationship in all these distribution things, okay, and that's why it's natural. So that's why you can ask questions that why we are suddenly seeing y by x, because it comes out naturally in this aspect. That's why we are seeing it Cauchy, okay. So all the easier questions that why it's coming out to be Cauchy, why it's coming out to be that way, so essentially everything gets cleared, okay. And similarly, you must be knowing if 1 by Cauchy is also Cauchy, because you can see in the theta now in this aspect. This will also be Cauchy, right? Instead of seeing in this manner, you can see in this manner. So essentially, 1 by Cauchy is also Cauchy. So you can visualize Cauchy distribution now. You can visualize chi-square now. You can visualize uniform is much more visualizable. Normal now, okay? So essentially, these are the connections. And once you know this connection, it will be helpful to applying problems, okay? And before ending, I will give you a little bit of problem, a food for thought. So lots of food for thought. You can check our the link of this problem written in LaTeX in our website of cheenta.com. And the food for thought is this, pardon my bad handwriting, that if x follows Cauchy 0, 1, then prove that twice x by 1 minus x square follows Cauchy 0, 1. In fact, it also implies that if tan theta follows Cauchy 0, 1, then tan of twice theta follows Cauchy 0, 1. And in fact, tan of 2 to the power n theta will follow Cauchy 0, 1 for all n. Okay, very beautiful result. I love this. So if you prove this part, so there's also a result that if sort of this is Cauchy and this is invariant, then this sort of Cauchy, there's a I'm not studying the result, but there's a result. There's a result between this, like just like you know the normal random variables result, that like multiplied normal random variable result is that y1 y2 dot yn is normal, multiplied normal if and only if all the linear combinations of this is normal. Similarly, there's a relationship between Cauchy. So therefore, the takeaway of this today's lecture, today's video is that this is the sort of connection between normal, Cauchy, chi-square uniform. That is the most important thing that you should learn from this video, okay? And will never forget in your life. Okay, thanks for staying till the end, and please subscribe to our channel, Cheenta Statistics channel. If you like this, don't forget to like, share, and comment your views. In the comment, mention your solution of the problem, the food for thought, and do not forget to check our website www.cheenta.com. See you in the next video. Stay tuned. Stay blessed.